Howdy, my name is Paolo Francisco, and I'm a student at Georgia Tech working for Dr. Ching Chu this summer. My project involves developing an automated method to analyze optical images of the fragmentation pattern in 2D materials that are undergoing strain. To begin, we'll be looking at the motivation for this project, which specifically involves the electronics-focused reason to study fragmentation. We'll then delve into the program, which begins with a user-guided image preparation process, followed by the automated algorithm itself. We'll then discuss the uses of the results of this program, as well as our next steps. So like most materials, we know that the conventional silicon-based computer chips can fragment. This also occurs in lithium-ion batteries. And so the future of electronic materials actually is in 2D ones, like graphene. And because of the behavior, the fragmentation behavior of the 3D predecessors in these applications, we expect that the 2D materials also undergo similar cracking patterns. And so to the right, you'll see actual images of 2D materials that are in fact undergoing fragmentation due to strain. The reasons it is important to understand fragmentation behavior kind of come from two different perspectives. The first being pretty passive. Basically, we know that 2D materials are known to be useful, that have high strengths and high conductivities, and it would be very helpful to help prevent fragmentation from occurring in the first place. However, at the nanoscale, in the more active sense, we see that some properties are actually size dependent. This allows for novel applications for graphene or other 2D materials simply based off size or shape. As you can see here, nanoribbons of graphene actually have semiconductor properties and higher mechanical strengths and chemical stabilities, as well as biocompatibility. So basically, looking at fragmentation, understanding it may help us to find newer applications for graphene of different shapes and sizes. A complete analysis of fragmentation yields information about the statistical and interfacial shear strengths of the material, both of which are important in understanding mechanical failure simply because they're implicated directly in it. This type of analysis, however, is pretty tedious. It's very labor intensive to conduct manually because it involves layers of analysis being done for multiple levels of strain. That's just the sheer mass of how much needs to be done is tough. So of course, like with most problems nowadays, automation is what would significantly accelerate the process and facilitate a more efficient analysis. So my objective for the summer was to automatically determine the average ribbon widths of the fragmentation pattern. For example, here in this image, we see that the white ribbon is the 2D material. And so I'd be measuring the widths, the average width of all of these ribbons all the way down. The black part is just the gap in between these ribbons. It would basically be the substrate that the 2D material is being layered on. So I wrote this program in MATLAB. The user first inputs some parameters. The program then measures the widths of all the graphene, and the resulting average width will then be used in mechanical analysis via a shear lag, basically a stress prediction model. So as far as the image preparation process goes, the user can prepare the image by first calibrating the scale bar. Then by cropping the area of interest, they can set color calibration, which is the most important part because this determines how the algorithm will see each pixel as to how it will decide if it's part of a gap or part of a ribbon, as well as setting size limits. This is important for accounting for defects for any of these substrate pixels hidden inside the ribbon pixels, as well as any ribbon pixels inside the substrate pixels. This will help account and make sure that those defects aren't ruining our measurements, and we'll talk more about that later. So the program takes these inputs and determines the widths. In our initial algorithm, it would basically sweep across the image row by row, pixel by pixel, and keep a cumulative count of gap and ribbon pixels. And as you hit certain criteria, certain minimums, or hit like a gap or the end of the row, you would then record the appropriate width. So looking at the algorithm as like a decision tree, you can see how like branched out it is. This is kind of due to the having to account for all the defect pixels. But essentially what the algorithm does is simply count if each pixel is part of a ribbon or a gap. The branches are caused by having to check for all the criteria of when exactly to record a ribbon width as actually being a ribbon, as well as when to combine any defect pixels with the surrounding larger portion. This is the continuation of the decision tree that is for the algorithm, just showing how much nuance there is in using this pixel by pixel approach. So after testing multiple images of different strains, we found that the histogram of distribution, the distribution of the widths had lots of low micron measurements, which is not what we expected or want, because this rectangle alone should be 80 to 90 microns. And you see that here the range of the distribution is from 0 to 10. So clearly the defects and some other issues are messing with the algorithm. So basically what I did to troubleshoot was create some synthetic images to try and find cases that were outsmarting my algorithm per se. And so after going through this, I was able to whittle down the number of low micron widths, but while also increasing the number of high widths. So we expect, as you can see by this top box, a high negative slope and a low negative slope when you look at the graph of width versus strain. And you actually see that relationship here for our current algorithm. So you're starting to feel pretty good. However, after further thinking, we decided that accounting for the defects during horizontal scanning, checking at every single pixel for if we should record the width or if we should count this pixel as part of a defect seemed a little bit inefficient just for how many criteria needed to be checked at every single pixel. So we decided to take a different approach, a much more simpler algorithm. As you can see here, the tree isn't 2 slides long. It's just a cycle with basically 3 steps. So basically what this algorithm does differently is that it first measures all the widths and the gaps regardless of size. Instead of accounting for defects at each pixel, that accounts for defects based off like an array of measurements. It accounts for based off like the defect input, the minimum width input from the user. It adds these measurements together based off their size. So to give a little example case, if we take a small portion of an image, the first thing the program would do is measure all the widths and the gaps in the image, as you see here. We'll then take into account the minimum gap width entered by the user, which is 5. So the program would automatically look at this and see here that there is a 5. This acts as a breakpoint. So basically just gets rid of this defect and does not think about it anymore. And it then goes to each remaining section. In each section, it adds up each of the ribbon widths, as well as each of the gap widths. I guess pixels is the proper term. So here you would find 8 ribbon pixels as well as 2 gap pixels. And here you would find 6 ribbon pixels and 2 gap pixels. What it does then, the only decision it has to make is that if there are more ribbon than gap, it is ribbon. And if there's more gap than ribbon, it is gap. So if there's 8 ribbon pixels here and 2 gap pixels here, and the 2 gap pixels are counted as defects. So you would sum this together, and the resulting measurements for these sections would be 10 and 8. So looking at our results, we found significantly less small ribbon widths than before. So if you look at this previous algorithm, we see the low bias, but we've seen a large improvement with our new algorithm with this histogram. You see that the distribution is entirely different. It's focused more around this 20 area, which is more realistic just simply by taking into account this is like 80 and including some estimation across the sizes of these other images. We'd expect this to potentially be the case. It's just much more realistic as far as the distribution goes. So we feel very good about that, especially the number of measurements alone actually stands out. Here there were a lot more measurements than there should have been, and here there were only about as many measurements as like 3 to 4 ribbons per row and how many pixels there were. So as far as the future plans go, I will be applying this program to all of the images and doing the same overall width versus strain plot, and then we'll verify the efficacy with a human analysis. The average ribbon width will then be used in further mechanical analysis based on the Streetlag model and the determination of the Weibull modulus, which is basically a parameter that expresses the shear strength of the material. The analysis will then be expanded to a 2D bilayer case, basically involving 2 layers of the same or different 2D materials stacked on top of each other. So with that, I should mention that this project was supported by the Department of Energy, the National Nuclear Security Administration, or NNSA, under award number DENA 0003857. And of course, I'd like to thank my mentor, Dr. Tu, as well as the coordinators for this program for making all this research possible. Thank you.